Okay, this is 1.3 homework. Problem 1, piecewise function. It says it wants the first part when x is less than or equal to 2 to be a parabola that opens down, shifted up 1 unit, looks like this one. And then it wants it to be the line when x is greater than 2. So that's A. Next one, it says when x is less than or equal to 1, it's just a line, y equals 1. Looks like this. And then when x is greater than 1, it's the line x plus 1, which has y-intercept of 1 but goes up. So it'd be this one, C. Next one says it's going to be the line 2, just a horizontal line, y equals 2, x can be anything. And then that's only for when x is less than or equal to negative 1, so that'd be this one right here. And then it does say it's a parabola after negative 1. So that'd be D. Which makes this B. Okay, I know we're getting into transformations already for the next problem too, but that's what we need to do. We're going to look at the graph, this absolute value function, and then what happens if it's made a little more narrow. So this one goes through the point. That's the point 1, 3. If you click on the graph, it'll get bigger for you to see, but that's the point 1, 3. So you want the absolute value of, you want a 3 here, absolute value of x. So that when you plug in 1, you're going to end up multiplying by 3 to make it steeper. So you get that point 1 comma 3 out of that. So that goes in here as 3 absolute value of x, like that. Same thing here, only this one's been reflected over, and that's the point 1, negative 2. So this is going to be y equals negative 2 absolute value of x. The negative sign flips it over the x-axis, and the 2 makes it a little steeper. So you can enter that in here. Next one, the parent function is y equals x squared. This parabola gets shifted over 1 to 3 units, so it's going to be y equals x minus 3. When you subtract a number from x, it moves it to the right. When you add a number, it moves it to the left. Next one's been shifted up 1 unit, so we're going to do y equals x squared plus 1. That moves it up. When you add outside of the function, like over here, not inside the parentheses, but outside, that will move it up or down, depending on whether you add positive or negative. Okay, next problem is a piecewise function. It says let f be 7 minus 12x if x is greater than or equal to 8, and 64 minus x squared if x is less than 8. It says find f of 12. F of 12, we got to use the top part because our number is bigger than or equal to 8. So we plug it in and we get 7 minus 12 times 12, which is 7 minus 144, which gives us negative 137. And then we want to do f of 4. 4 is less than 8, so we got to use this bottom one. So 64 minus 4 squared, which is 64 minus 16, which gives us 48. Okay, next question is a little bit weird, but it says, looking only at the values of x to the left of 8, what would you expect to be? This would make more sense if you're looking at a graph. You know, 1, 2, 3, 4, 5, 6, 7, 8. Greater than 8, it's a line with a y-intercept of 7 and a negative slope, so it's like, I don't know, a line that goes down like that. And this one is a parabola that opens down and shifts way up to 64, so I don't know exactly what this looks like, but it's shifted up 64 units and goes down, so I don't know, something like that. It says, looking only at the values of x to the left of 8, what would you expect f of 8 to be? Well, left of 8, you'd use this part, so you'd expect it to be 0 at 8. This must be what the parabola goes through 8, so I didn't draw up the path. The parabola goes through 8 right there. So it must look something like this. And then it says, looking only at the values of x to the right of 8, what would you expect f of 8 to be? So, you know, if you were to use this parabola and plug in 8 then, 8 times 12, 7 minus that would be negative 89. So it turns out that this thing goes down to negative 89 if you were to use the wrong part of this branch. Next question, what type of discontinuity does the graph have at negative 4? I don't know why that's there, ignore that. But at negative 4, it goes from negative infinity, and then jumps all the way to positive infinity. So that's infinite discontinuity. And then at -2, you have a hole, so that's removable discontinuity. Next one, x equals 2, that's removable as well. And then the next one, x equals 4, it jumps from here to here, so it'd be jump discontinuity. Okay, next question then says, suppose we have two functions, x squared and 2 to the x, are drawn on the coordinate grid, where the unit of measurement is 1 inch. Find the distance of 2 feet to the right of the origin, the height of f, but the height of the graph G is about 265 miles. Okay, so let's do that real quick. Okay, so we have, two functions. We have the quadratic, and we have the exponential function. And the exponential function grows really fast. Okay, so it gets really steep and goes straight up, and my graph doesn't show it that well. But if you plug, make it 1 inch and you're going out 2 feet to the right, 2 feet to the right is like out here, right, which would be 24 inches. You're plugging in 24 into this function. So we're basically trying to find f of 24, which turns out to be pretty big, 576. So on the parabola, you're up, if you go out 24 inches, you're up 576 inches, right? But on the exponential function, if you go out 24, you're up this number, which would be 16 million inches, about. So exponential function grows really, really fast. But they're asking for the height of f, so you should be able to enter in 576. I'm sorry, we have to divide this by 12 actually because it wants it in feet. If you check this out, it asks for feet, so divide by 12. Okay, the next problem gives us this function and wants us to give us the domain. So we know what's inside here. 16 minus x squared has to be greater than or equal to 0 because we can't have negatives underneath radicals. So if you subtract 16, you get negative x squared is greater than or equal to negative 16. If you divide through by a -1 or multiply by a -1, however you want to do it, that gets rid of the negatives, but you have to switch the inequality because whenever you divide or multiply by a negative, you have to switch the sense of the inequality. Now square root, and you get x has to be less than or equal to 4. That's the positive, but you also have to do plus or minus here. So you have to do x and you have to switch the inequality. X is greater than or equal to -4. So we would do -4 to 4 here, and we can include these points because that just gives us 0 if we plug in 4 and -4. So then the range, it helps to take a look at the graph of this as well. If you graph this on decimals, you'll see this right here, which makes sense, -4 to 4. And then it goes up to 4. So the range is from 0 to 4. And if you're not sure, you can get that from algebraic reasoning as well. Because you look at the smallest value. Smallest value is when x is 4, in which case you get 0. And the largest value is when x is nothing, because then you have this, right? 16, square root of 16 is 4. So it goes from 0 to 4, you can include those. Okay, next one says find the domain of this. It just wants the greatest x value in the domain. So basically we know that what's underneath this thing has to be greater than or equal to 0 because we can't have this negative. So if you multiply both sides by 9 plus 2x, this cancels, and it doesn't matter, this is just 0 still. So that gets rid of the bottom. And then subtract 10 from both sides. -4x is greater than or equal to -10. Divide both sides by -4, and when you do that, you do have to switch the inequality and double negative go positive. This turns into 5/2 though. So x has to be less than or equal to 5/2, so 5/2 goes here, and you can verify that with the graph as well. Not that graph. You can verify it with the graph that the greatest point is at 2.5. Next problem wants us to give the domain and range. First of all, domain, we can't have negatives underneath the radical, so we have to have x be greater than or equal to 0. That's the same thing as 0 to infinity. We can have 0 though, that's okay. So it would be 0 to infinity, the bracket, the parenthesis. The range then, if you can plug in 0 as your smallest value, that gives you 2 for y. So it would go from 2 And obviously anything you add 2 to is going to get bigger, so we can go all the way to infinity. We can have to, because if we plug in 0, that's what we get. We can't include infinity though, because you never include infinity. Next problem wants the domain and range of a piecewise function. All x's are okay. You can have any number bigger than 2, you can have 2, and any number smaller than 2. So we can do all real numbers here, negative infinity to infinity. You might want to spell out the word here. And then the range, we have to look at these. This line right here for less than 2 has a positive slope, starts at negative 14. And this other line has a negative slope. All right, so what we can do is we kind of got to look at both of these. So when x is less than or equal to 2, right here, this part is a line. Let's look at what it looks like at 2. It would be 2, you get negative 6. 1, 2, 3, 4, 5, 6, which is right here. That's a closed circle because you can define it at 2. And then this thing has a positive slope, but we only want the part that goes down like this because we only want the part to the left. It has a y-intercept of like negative 14 down here. And then this line at 2 would be 7. We got 1, 2, 3, 4, 5, 6, 7, and it'd be an open circle. This one does have a negative slope. It goes down 1 over 2, so it goes like this. So, if you look at the range, you can have all values you want. This, if you look at the shadow on the x-axis from these, this one keeps going, so that shadow is going to be there. Those y values will all be included. It's just the y values that are above 7 that won't be. So the range will be from negative infinity all the way up to 7, and not including 7 because that's an open circle. So that would go here. This one looks pretty easy then. The domain of f, it looks like it goes from 2 to 14, and you can include both those endpoints. And then the range looks like it goes from 2 to all the way up to 10. So 2 to 10, you can include both of those because the highest value is actually 10 up here. Next problem wants to find the domain of each function. You can graph this if you're not sure what they look like. It can be a little confusing, but basically this first one, you can stick anything you want in for t. Because, if you stick in a really big positive number, then basically, you have 1 over e to some really big number, which is just, approximately 0, which is fine. You can stick in a negative number because then you'll just get, e to the positive number, which is, you can take the sign of any number you want. So that's just all real numbers. And you can see that from the graph as well. If you look at a graph of that, it's this blue one, and then it widens out right here, basically. You can stick in all the domain values are there. The next one is this square root function, which has been manipulated a little bit. And it looks like it's got to be all values less than or equal to 0. And if you're not sure, once again, what's under this radical has to be greater than or equal to 0. So you can solve this. It's a little bit tricky. But it turns out that, for this one, t has to be greater than or equal to 0. I'm sorry, less than or equal to 0. Because if you solve this, you subtract 1, you get negative 2t equals, or I'm sorry, greater than or equal to negative 1. Divide by negative 1, and you change the sense of the inequality. Now, what would you raise 2 to get 1? That'd be 0. So t has to be less than or equal to 0. All right, the last problem gives us a function. It says it's quadratic when x is less than 0, so that looks like it qualifies so far. It's a square root function, so that's good. Whenever x is between 0 and 4. Then it's a line with a slope of 1/2 and a y-intercept of 0, so that's not right. So we have to look for something similar with a line right here. This one has a slope of up 1 over 2, up 1 over 2, so it would be d. All right, I hope this helps.